Hey, good afternoon. Welcome to my TheiaCon talk. I'm here to talk about zero install and for embedded C and C++ development. Running GDB in the browser, and we're going to talk about some WebAssembly. So my name is Jonah Graham. I work for Kitra Coders, and I'm an open source advocate. I've been involved in the Eclipse community for a long time. I'm an Eclipse project lead on the Eclipse CDT and Eclipse CDT Cloud projects. And I'm looking forward to showing you some of the work that's been going on for the last number of years in this area. So when I say zero install, what do I mean? Zero install is generally speaking, running the code, running the program without having to install any tools. Typically, that means running in a browser. One of the ideas, it gets rid of it works in my machine issues, no setup, no overhead. It's not unique to C++, but for embedded C and C++, it is special because in addition to all the code editing and building that works like other languages do, for debug, we actually have to connect to real hardware that might be on your desk or somewhere else in the cloud. Typically, real hardware uses technologies like JTAG. So we have to get zero install, use WebUSB to connect those web browsers to hardware. So I'm going to take some time to just go through some of the design progression from the beginning to where we're developing now. So step zero, before we even start any zero install, is the traditional ID. Download Eclipse, install CDT, install your debugger, your compiler, and everything else like that. So everything is installed on your local computer. You got your laptop on the left and your development board on the right. You install all the tools, J-Link to connect them over USB, and you're good to go. So there's a big pro of a traditional ID. If you're an ISV or something like, or an embedded company that you're trying to do, it's like the big advantage of traditional ID is we have it already. Absolute maximum reuse. It's pretty secure because it's as secure as the rest of your computer is. We'll talk more about security as we go through the presentation. It has a big advantage that you can use whatever language you want for different parts. You want to write your GDB server in one language and your ID in a different language. You can do that quite straightforwardly. And it provides absolute maximum control for the user. The user gets to choose exactly which parts they have from where. Now, the cons of the traditional ID is it's the complete opposite of a zero install. That maximum control for the user that we see as a pro is actually a big con as well. It leaves so many more things to stumble on. It's left for users to have to manage all of those interactions. Like, I have version 3 of a driver installed, and this program needs version 5, and how do I make these things work together? So the very first step on getting to zero install is let's just move everything into the cloud. So this is an ID in the web browser. The browser is just rendering the UI. So we split the traditional ID. We run the code editor in the browser, and all the debug logic, that all runs on the cloud machine. The board can connect to the cloud through unsecured connections, or it can do some secure proxies and tunnels, and there's some pretty neat tools for that as well. So what we've done is we've hoisted up a bunch of the software off your local computer and put them in the cloud at the top of the screen. Then your web browser runs, and your code editor and all your actions initiate in the web browser, but all of the logic is in the cloud. It does mean you have to connect to your board. Somehow you have to get from that cloud to your development board. A common way to do it is using GDB's remote RSP protocol. So GDB server will run on the development board, and the cloud can connect to it. So to give an idea of what this might look like, I have bit of a blast from the past of Che running even before Theia was integrated in Che. So in here, sorry. So in here at the bottom of the screen, you can see that we're actually just logging into the board and running GDB server, opening up a port for the program. And then when we start our debug session, we're just going to be connecting to that port at that IP address. And as you see, debugger is connected to that IP address and port. And then we can single step our program as normal. Now, the single step speed in this demo is pretty good because this is a development environment where I have the cloud really just running in Minikube on my own computer. So what are the pros of running in the cloud? Well, one of the biggest pros is almost the entire debug stack doesn't have to be changed at all to work this way. So if you're an ISV, embedded company, something like that, you can quickly ship something with this. There isn't any duplicated effort because the desktop and the cloud teams, they get to do things like share the same GDB executable. But the cons, and as you see, I had to make the font a bit smaller to fit all what I think are the cons on the list on the screen. So one of the biggest cons is that you kind of need a big board running GDB server. By a big board, I mean something that is able to run GDB server itself on the board. So in the example I showed, I had a board that was running a full Linux install, so GDB server could run on it. Or if you can't run a big board, you need to do some other work so that your board can talk onto the internet through proxying or something like that. With the JTAG connection, no internet is needed. So that's the extra complication here. Now, as soon as you connect the board to the internet, in practice, it starts being a little bit insecure. Now, it's possible to make it secure, and some newer tools make it easier. But in practice, unless you make it really easy, users are just going to expose those boards to the internet because it's easier and faster. Another big con is that it's very slow. A single UI operation, like doing a single step, it might only require a couple of round trips from your browser to the cloud. But as you go down every layer in the debug stack, you require additional operations. So one round trip for a single step in the browser. For the debug adapter level, that might be 3 or 4 operations. As you get down to the MI layer that the debug adapter talks to GDB with, that has a few more round trips for every command. And then we get to the RSP layer. That could be dozens of round trips that have to happen. So if you have a local setup where the cloud is in the same building as you, that could be fast enough. But if you have a data center in another country or another continent, you can be up to many seconds for a single step. The final con I have listed here is about the setup required for a user. A lot more about the system needs to be understood for the users. It's much less plug and play. So that first demo I showed is a nice old one, but in the context of TheiaCon, I wanted to show what that looks like a little bit more today. And so Renesys have this product based on Theia that's called Quick Connect Studio, allows you to design your system, like literally drag and drop building block boards together, and then you can build and even debug with this system. So here we're going to generate the project, and this is using what I was talking about before of a lot of your tools just get to exist in the cloud. So what's actually happening here is we're using traditional CDT to actually build the project. But at the end of the project, if you want to do advanced debugging to your local board, what you need to do is you actually have to download the project and import it into the Eclipse as installed on your computer, which negates a lot of the benefits of having a zero install system if you still have to install the debug stack. So you download this project here. If you open it up, it looks like just a normal Eclipse CDT project that you can debug with. So the next step, let's do some local debug. We'll do a little bit of install, but not zero install. So rather than trying to run the debug stack in the cloud, we're going to start running the debug stack on the local PC. We're going to use something like a WebSocket as a typical way to get from the browser to your local host. On the local host on your computer, you need to run some kind of a controller that can bootstrap up the debug session and be the connection for the browser to your local machine. Now, the controller can be as simple as some instructions and using an open source tool like WebSockify that converts the WebSockets to TCP, or it can be a full program that handles all of this bootstrapping for you. So what this looks like is we've moved all of the debug adapter and the GDB server, all the JLink, they've come back to being local programs, a bit more like in the traditional ID setup. Your build, compile, that still can just run in the cloud. You don't need to install those tools. And the web browser just has to have some way of getting out of it, staying local to do, for example, in this shot, use the debug adapter protocol to have the front end talk to the debug adapter. Now, the pros for this should be pretty obvious by this point, but most of the debug stack is shared with a traditional ID. It's the same GDB, exactly the same one as in the first version, same platform support. Single step performance, that's pretty much resolved because everything is now local to your computer. And a lot of the security issues have been resolved here because boards now only need to be connected to the local host, not the entire internet. Now, there are some cons. We aren't anywhere near zero install. So for a first simple example that I just showed here, this is the programs we have to install. We have to install Node to run the adapter. We need the debug adapter itself. We need some kind of a proxying tool, either WebSockify or we're going to write something custom. GDB server, and JLink drivers or whatever you're connecting to the actual board. It's still pretty complicated to run, either manually using WebSockify, or ideally, if you're looking at doing this as an ISV, is you want to have invest in a custom controller. There are security considerations left. We've reduced the attack area, but the main thing we're doing is if we're letting the users run things manually, they are going to leave things too open, make it too easy. If we create a controller that can handle this, that will be like a WebSocket server that's running on your local machine, hire someone who understands the web security well enough so that only the websites that you intended to be able to connect to it are able to connect. There is some new code required as well. You can't just completely reuse the traditional ID because you do need to have some way of getting from the browser out, and that means modifying the in-browser ID. So here's some screenshots from a version that we wrote based on Che. So we do a debug using the debug adapter. We modified Theia at this point, I think it was, to actually be able to keep the debug connection within the browser. And then we have this little tool that we call the USD debug. It's got a little icon that runs in your taskbar. And when a connection is made, will let you know about the connection made, and it will allow you to do debugging. The little USB debug tool will start up the debug adapter, GDB, which will start GDB and GDB server in sort of the traditional way. And you can see that JLink is up and running once the debug session is running, because that's how the board is connecting. So kind of a sub-step here. Let's just install less on the machine and put more into the browser. And I'm going to go through some examples of this. These are less install. We're not at zero install yet, but we're progressing in the right direction. So, for example, we're going to move the first one we're going to move is move the debug adapter. So instead of speaking the debug adapter protocol from the browser to the local machine, now you can speak MI. And this is where JavaScript comes in to help, right? And I used to make jokes about the JavaScript developers, and now I've become one. Although I still highly recommend using TypeScript, something else with types, so that you can have a certain amount of sanity in static analysis. So to move the debug adapter to the browser, it is that easy first step. In our case, and in many cases, the debug adapter is already written in a JavaScript or JavaScript compatible language. So in our case, TypeScript, already transpiled to JavaScript. We do have to update the launch mode and communication methods. When we first wrote this, VS Code API didn't have support for this, but now VS Code API allows us with to doing local launches using web extensions. It makes it much easier to handle this. A random piece of advice is debug adapters in their traditional design run as independent processes, which makes it really easy to clear their state, because as a process is killed and restarted, no state retains. Running it in a browser, more of the state will be retained. So some care needs to be taken when moving that piece of code around. So as a next step, let's just move a little bit more into the browser. The next one we moved in is let's just put GDB in there and have GDB speak to GDB server using a WebSocket, speaking its RSP protocol. And this is where I get to quickly run away from JavaScript again, because GDB written in C and C++ isn't strictly JavaScript compatible. But by using WebAssembly, we can get there. So WebAssembly, it's a binary instruction format for stack-based virtual machine. But what it really means is it's a format that can run in the same engine as JavaScript. And many languages, but for my interest, C and C++ can be compiled to WebAssembly. For this project, we used nscriptn as a tool chain, an SDK to convert the GDB program into WASM and run it in the web browser. So to do that move, we used mscriptn. That made it relatively easy. All we had to do was run the special configure and make wrappers to em configure, em make GDB. But then we had to work on the interface to the external world. So GDB expects to run on like a POSIX or Windows type machine, and so we had to have different ways for that communication to happen. Now, the two main communication sides interfaces for GDB are the serial stream from GDB to GDB server. It uses RSP, and standard in, standard out to communicate with the user or the debug adapter. So on the RSP side, what we did is we modified GDB to add a new connection mode for GDB. Anyone who's used GDB will be familiar with the command target remote, and then you give an IP address or a serial port, or sometimes some additional options. We added a new option, which is target remote WS://, which is a typical way of saying a WebSocket, and that will fall into the WebSocket implementation of making a communication. So a user could type target remote WS:// and give it the IP address and port to connect to the running GDB server. And then we use WebSockify at the other end to convert WebSockets back to normal TCP to connect to GDB server. And that way GDB server doesn't need to be modified. Of course, GDB server could also just implement a WebSocket server. On the GDB standard in, standard out side, we want to have some buffers that would allow better communication between the MI and from the debug adapter and GDB. So we focus on having a buffer that allows the reads and writes to happen without delay, as long as the buffers aren't full. And also we implemented some. We also implement support for polling. So the poll and select APIs in C, and that polling also supports timeouts. These are all parts of how GDB uses to communicate to the rest of the world. So here is an example of using GDB running in a web browser. In the top left we have GDB running in CLI mode, and you can see we can interact with it. Printed 4 plus 5, it's going to print 9. In the top right, I have the webcam focused on a development board. In the bottom right, we have WebSockify, which is going to take going to serve on 2345, port 2345, and forward that as a regular socket to 2331. 2331, for those in the know, is the default J-Link GDB server port. And over here we have the J-Link GDB server connected to a board, waiting for a connection from GDB. So you see normal interaction with GDB works. I did show this version, I use an older version of GDB. And I did a target remote ws://localhost 2345. As you can see, all of this came to life. I issue monitor reset, and you can see down here, J-Link received that and did a target reset, and then put a hard rate breakpoint, and then just press continue. The hard rate breakpoint is in the middle of the loop on the blinky, and as you can see, every time we continue, the LED turns on and off. And down here, you can see how much communication has to happen for every single continue. So step 3, this is where we're really trying to get to. Local debug with 0 install. And to make that possible, we use WebUSB. So we move more and more into the browser. And the last step is to actually get the hardware connection to the browser. Now we move GDB server at this point into the web browser because in our case, GDB server was linked against a J-Link library rather than being separate programs. So we pulled those in as one step. So that's what this looks like in a graphic. We still have this stuff running in the cloud, but on the computer, we no longer have the part of the picture with a local install. All of the code is running in the local browser, and the web browser is connected using WebUSB directly to the development board. So WebUSB and everything within a web browser environment does expose us to a real challenge. Synchronous versus asynchronous programming models. So WebUSB and everything in the browser all uses asynchronous programming models. Typically, C and C++ programs will use some kind of a synchronous programming model. And we need to be able to connect that synchronous program to the asynchronous APIs. We want to do this because the goal is to be able to compile GDB server to use it without having to do any, or at least not a lot of modifications. So to do this, we're using a bunch of APIs that a web browser provides, using web workers, atomics, and shared array buffers. And to do this, we can actually pause the WASM code while asynchronous operations happen. Now that allows us to do something like take the WebUSB API for transfer in, and it can be operated in synchronous way. So instead of having a callback when the transfer is complete, we can pause the WebAssembly until the transfer result is ready, and then continue the C code. Now we took the synchronous asynchronous connection, the buffers, and other parts, and combined them into a package that we called web kernel. Now the web kernel provides OS functionality so that we can do synchronous programming within a web browser context. Now, the web kernel is made up of three main components. The first is the I/O buffer, and that's for handling streaming interfaces. We don't want to block the C code if the buffer isn't full when it's just doing a write. We want to let that asynchronous behavior continue while maintaining the semantics that the C code expect. We implemented an RPC, and this RPC goes basically between two different web workers. So you do an RPC call from the C code to the server running in another web worker, and it allows you to pause the calling code until the RPC call is complete. On the RPC server side, it can run normal asynchronous behavior, like actually doing the transfer in, getting the result, on the callback, returning the RPC result. And the last part is the launchers. So we want to launch a WASM program like from a VS Code API web extension, but we want to launch it quite similarly to how we launch a child process in Node. So that's the last piece of the puzzle to make the web kernel complete. So we're at zero install. It's gives a user first a good experience. They can visit a website and just start the IDE, code something up, plug their board in, and press debug, never having to install anything. It simplifies testing for ISVs and or embedded companies that are shipping this, because it isolates you from all of anything else that anything else that users might have on their machine, and it resolves almost all the security issues. We're moving to rely on the web browser security model for WebUSB. We don't have to implement anything additional ourselves. Now, there are still some cons for zero install. Now we need a version of the code that could run in a web browser. So either this means using WASM and keeping the same source code, targeting both formats, or you might even want to rewrite parts of your debugger stack in JavaScript. Browser support is important to make this work. So WebUSB at the moment is only supported in Chromium-based browsers. Now we get cross-platform support because Chrome is based on Chromium, obviously, and works on all platforms. Edge works on platforms, but critically, Firefox, for example, doesn't have WebUSB support today. Moving into browsers, browser evolution is fairly fast. You can take a program compiled in 2001 for Windows and it still works in 2024. But we need to constantly retest our debug stack on new versions of browsers to make sure it still works. So it does allow us to write once and run it everywhere. The same code works on Windows, Linux, whatever, because it's all running in the browser. But you still do need to test it everywhere. Some of the behaviors of WebUSB differ slightly between Windows and Linux, for example. So in summary, we're basically at the mercy of the browser ecosystem, which is somewhat of a con here. So here's a little demo of doing debugging within the browser. So when we press play here, WebUSB pops up and we can connect to the board. And so we're connecting to the board, and you can see we have communication happening there with a board that's plugged in. If we just accelerate to an interesting part of the debug thing. So here we have a call stack for where this breakpoint was, or where we paused, I can't remember. And you can see here the list of registers, which is I find a little bit slow to collect at the moment. So it's an area we still have to look into for where in the stack that's slow. And you can see the registers, and that works as expected. And you can see that if you look at the site information, we have a JLink USB device that's connected. So the user has visibility and control of how things are connected there. In conclusion, zero install for embedded C and C++ development is coming, and it's possible for embedded tools. The key enablers for this are WASM, mscriptn, Web Extension API, and they all make this possible. The ecosystem is still evolving quickly, so it's quite a challenge to be involved in. But that challenge is also creates a huge opportunity to get the best options as we progress this forward. So thank you very much for coming to my talk today. I appreciate it. If you have any questions, want to follow up, best way is to reach out to me by email, my email address there, and I look forward to answering any of your questions and seeing you at future conferences. Thank you very much.